So there's two ways to look at this problem. Oh, somebody broke this thing. Come on. There's two ways to look at this problem. I could say, suck it up and do it. I should figure it out. So if you look at your calculator real quick, look at your calculator. If you have it there with you, see the sign button? What's right above it?
Inverse sign button.
Right. So we know how inverse functions work. So since the sine of pi over 6 is what? What's the sine of pi over 6?
It's 1/2.
What would the inverse sine of 1/2 be?
2.
That's crazy. No, don't be doing that to me. Inverse functions, they take you right back to where you came from, right? So since the sine of pi over 6 is 1/2, the inverse sine of 1/2 must be pi over 6. So if I had a situation where I had sine theta equals 0.89, how could you figure out what the angle is?
Take the inverse of.
Over.
What would you do to both sides?
You take the inverse of.
You take the inverse sine of both sides. So what that would look like, let me make some room here. You would take, and this is actually nothing specific to trig functions, is it? This is how you solve any equation. You do the opposite of what's there, so you can strip it away. So if I apply the inverse sine to both sides, these are going to cancel. So then I'll know the angle is that, and if you put that in your calculator, depending on what mode you're in, it'll spit out radians, but if you change over to degrees, it will spit out degrees. So what'd you get?
52.87.
So that's obviously degrees. And you can convert that to radians, or what's it say in radians if you did it in radians? Does anybody? We'll never know. 1.09, blah, blah, blah. Right. Okay. So, very much like, remember when we learned logs, and I kept saying a logarithm is a what? What's a log? A log is a power. Right? So the output of log is a power because a log is the inverse function of the exponential, where the input's the power. Are you with me?
Yeah.
So the output of an inverse trig function must be an. What was that? What is that? That's an what? Angle. This is an angle, right? So since the input of trig normally are angles, in fact, pretty much always are angles, then the output of an inverse trig must be an angle. The angle that makes the sine become this. I don't know if that sounds familiar. I use that same kind of language when we were talking about logs. The power that makes the base become this. That's the inverse ideas almost always have that kind of phrasing to them because you've got to think backwards about them. Okay, so on one level, number 57, you could just say we can't do this yet because we haven't gotten to the inverse trig section yet. Because there is an inverse trig section in chapter 5 that I completely forgot about. I just didn't want to do 2 of them and I picked the 1 in 6. So that's one way. Or you could actually just do the damn thing because you have the inverse trig functions in your calculator. You could just solve it. So they tell you on that specific problem, number 57, they tell you the area and the area formula. And this is one thing I didn't talk about in class that I just left for you guys to look at. But real quick, if I had, let's say this is A and this is B, and this is theta. And I want to know the area of this triangle. Now stay with me now. We're about to derive a formula. So the formula you can use and the derivation you can hopefully absorb. What do I need before I can figure out the area of that triangle? The height, yeah, because the area of a triangle in general is 1/2 base times height. So if they don't give me the height, that used to suck, but now, what have I just created once I draw it in? In fact, the height is defined to be drawing it perpendicular to the other side. So it will always be a right triangle that you create within your triangle. So how tall is that? Yeah, you do.
Yeah.
What angle? What trig function do I use here? Why can't I use b for this?
Because it's only part of it.
Because that's for the whole triangle. What's the only thing I know about this triangle? Two things. That triangle has hypotenuse A, and I know the angle is theta, right? So what trig function relates what I want to know? Let me call this y for right now. So if I put h, it'll be a hypotenuse and trig. So yeah, sine theta is equal to y over a, so that means that y equals a sine theta. So that's the height, right? That's the height there. That's a sine theta. So what's the area of this triangle? It's 1/2 the base. D, okay. Times height. What's the height? A sine theta. So if you look on page 459, they do everything I just did basically, and they eventually get here. 1/2 AB sine theta is the area. So let's do the first couple steps in 57. 57, they tell you the area is 16 square inches. This is number 57, section 6.3. Area plus 16. They tell you that the two sides are 5 and 7. That's like these sides here. And they ask you what's the angle in between those two sides. So what's really cool about what we just did is it doesn't matter how I turn the triangle around. It doesn't matter which two sides I pick. I just always have to pick the angle that's between them. And then that formula is true. So no matter how your triangle's oriented, you don't care. You pick two sides and an angle in between them, and that formula works. Period. It's kind of crazy. So I just plug and chug, right? And the hard part about this, before what we're talking about this morning, is you had no idea how the hell to get the angle. You know, like I can solve for sine theta and see it's something stupid, 0.73, whatever, who cares? But now you know you just take one more step. You just take the inverse sine of both sides. So plug these in, solve for sine theta, and then take inverse sine. So let's try that. So it'll look like 16 equals 1/2 AB, so 5 times 7. So what's sine theta equal to? Don't give me decimal, give me that. Yeah.
29.14. Sorry.
So it's 32 over
17.5.
35.
So it'll be 32 over 35, right? Yeah, double to kill the 1/2. Cool. Gotta do something with that fraction. And now just take the inverse sine. So the reason, don't make this a decimal because you're rounding too early. You never round until the end of a problem. Ever. So here you got theta is the inverse sine, and you just put in your calculator, inverse sine, 32 divided by 35. And depending on what mode you're in, it'll give you radians, or it'll give you degrees, depending on what mode you're in. So whatever you get from that. That's really close to 1. And sine is 1 at pi over 2 at 90 degrees. So I'm thinking this should come out close to 90. What's it come out to?
66. Yeah.
Okay. Well, it's closer to 90 than 45. How do you like that? Theta equals 66?
66.
Yeah.
Where'd you get the 35?
Which one?
35. How'd you get it?
It's there. Oh, it's there. 5 times 7.
Oh,
I'm sorry, Jesse. It's like, where'd you get that from?
Oh, it's right there. Go ahead.
Yeah, it's just 5 times 7 from that. Yeah, cool. Okay, cool. How are we doing there? The nice thing with that is we just basically did a large part of the lecture for today, which is awesome.
Yeah.
Yes.
No, that means we'll move on.
No way.
I don't get it.
I'll tell you this. I will make this pledge to you. Actually, I already told somebody. I think I said this the other day to somebody. We're only going to make it up at 6.4. 6.5 and 6.6 are huge ideas. And I'd rather have the test next Tuesday and keep it Tuesday than push it back and include those two on the next test. Right? And I actually almost don't care what you think, but does that sound all right? I don't care because I'm going to do that no matter what. But I think you'll agree with me that's better. I'd rather have fewer topics on the test.
Yes.
Yes.
But then that means the next test is gonna have more, so is 7
Well,
and 8.
I'll just have to adjust. We don't even know. Well, I have to adjust that. And I've got the other second half of the homework stuff. It's not a half, but the second part of the homework stuff to give to you. So I have a lot of leeway in there.
Yeah, so I was just, is 7 and 8 gonna have a lot of big ideas as well? Chapter
The
7?
whole damn thing.
Oh, cool.
But the nice thing.
Just making sure.
No. The next couple sections are really based on trig. We get into more and more identities. There are roughly an infinite number of identities
Just roughly.
that you could use. Yeah. We're not. None of that we have to memorize, but we will have to prove them. Yes. 60. All right. So same section. I think that's got the same kind of problem. Yeah. So number 60, yeah, okay. This one looks freaky.
Oh, yeah.
And then, of course, I'm going to do the opposite because it's easier for me. Find the area of the unshaded region, right? Which really just means find the area of the circle and subtract that little piece off. So I can find that now. What do we know? Two things. One thing we learned today, and one thing we learned a while back that deals with areas that I'm mostly concerned with. How do you find that little piece there?
It's times theta by times the radius squared.
Radius squared's in there. So the area of the sector, the whole sector, right?
Yeah, 1/2 radius squared times theta.
I like it. And what's the area of this triangle?
Half.
Half AB. Same thing. We just figured it out, right? We just figured it out, just like 2 minutes ago. You guys with me so far? Now, what do you need for this, though? What do you need for this equation? I got theta, pi over 3.
B.
No worries. I need A and B. I've only got one, but of course, what's this?
Well, it's an exact 60, 60, 60. It's triangle.
Yeah, it's an
So it's
equilateral.
12 and 12.
Beautiful, I love it. But in case they didn't give me such a nice angle, this is how I would do it in general. But Chris just realized, if that's 60, do these have to be 60?
Yes.
Why?
Because it's an equilateral triangle.
No. You're trying to prove you're trying to say by using what you're trying
Well,
to prove.
because both the angles are the same. Too.
They have to be, yeah, these angles have to be the same. It's the way it was drawn. Neither one of them is a different situation than the other. So good. So you don't have to use that necessarily, right? You can realize that that side is 12. But how does that help you with the area? I'm not interested in the side lengths. I want to know the area of the triangle.
I don't know how to go.
No, that's
I did the-
that we do. This is the area of the triangle. So I can find that last side length easy. But that doesn't help me get the area of the triangle.
Don't you cut it in half?
You don't have to. We already did. So if I have, this is the triangle I basically have here, right?
Yeah.
I could cut it in half and figure figure out the height and all that stuff. But that's what I really want you to understand. That is what this does. This does that work. We did it for any triangle. So does it work for that one?
Yeah.
Yes. I like the way you said that. So, area of a sector is older news. Right? And I know the radius. I know the angle. The angle's already in radians, which is nice. So what's that going to be? What's the area of that going to be? 1/2, 144 times pi over 3.
Stuff.
Way to go out on the limb there. Yeah, 24 pi. Good. Which is roughly what?
75.
I got 75.3.
Blah. Now what about this guy? How do I set that equation up?
1/2.
Sine of
Pi over
theta, which is pi over 3. And what is sine of 60?
1
Beautiful, because it's closer to 90, so it's going to be bigger because sine likes y. So it's 36 rad 3, whatever the hell that is. Okay, good. It's less, thank God. If we would have gotten that more, that would have been a problem, right? The triangle should have less area than the sector does, because the sector has this little extra piece there. Let me stop there. The main part of this problem, we're not going to be done once we figure this out. We're actually going to have the opposite answer, really, in a way. But the first part of this problem was figuring out that little slice they left out. I got to figure out what that slice is. I look at this as a cookie cutter problem. If I figure out what the area of the whole dough is and then cut out the part I don't want, make a cookie out of it, I can figure out the area of the rest of it. Yeah?
How did you get the area of this sector?
So the area of a sector is this formula here that we talked about a while back. Right after we talked about the arc length, S equals R theta, we talked about the area of a sector of a circle. And that's what that is, 1/2 R squared theta. I showed you how it kind of relates to 1/2 based on type, which is kind of nice. Yeah?
So for calculator, when it says sine pi over 3, you don't want to put in a calculator sine 60.
For the area of the little.
Would that kind of mess it up?
No, for this problem, not really. Because I probably want to get it to decimals anyway, right?
I tried to work out.
Well, it depends on if you're in radians or degrees.
I was in degrees. Was that the problem?
No, and you put in 60?
Yeah.
Then you should get whatever the rad 3 over 2 is, which is roughly 0.8 something.
Yeah, 0.866.
So if you put sine to 60,
No, I did rad 3 divided by 2. I didn't have the parentheses around the 2. That makes sense.
okay.
But I get it.
So if I subtract these two areas, what do I get?
13.04.
And physically, what is it? Physically, what is it in my fixture?
Just that tiny
Just that tiny little piece. So can you get the area of the circle?
Yes.
Yeah, that's thank you. Please, dear God, ask me areas of circles, Jeff. Don't ask me areas of slivers of pieces of sectors. Shit. Area of circle, easy. Minus the area we get from that when we subtract, that's going to be the area of the shaded part, because the shaded part's everything else. So figure out what the area of the whole circle is. What is the area of the whole circle?
452.39.
Yeah, it's 144 pi, right? Which is whatever you just said. Minus the area of this little sliver, which is the difference in those two. We'll give you the area of the shaded part, because the only part they didn't shade was that little sliver part, right? So you first figure out how big that little sliver part, and then you can subtract it from the whole thing. Cookie cutter problem.
Okay. So the top equation is the whole triangle.
The top, this one is the sector.
Okay, yeah. Yeah.
So
no,
that one is going to be
Yeah.
the area of this whole
And
thing.
then you took out
This one is the triangle.
And
So when I
then-
subtract these, I'll be left with that little sliver. Subtract that from the whole circle, answer.
13.04.
All right, whatever the hell it is. At this point, I don't care what the numbers are. I care about the idea. You guys can get the numbers in your calculators. Yes?
Can you do part A on 70? That's 6
Oh. So that sort of reminds me of number 64 in a way. Oh. Yeah. Okay. Is that working?
Yeah.
Good.
It's just
So 70. Yeah, 70 gets a little bit freaky. And I lived this once. I miscalculated, bought a new bed. I had like an attic bedroom. And it wouldn't make the turn. The box spring wouldn't make the turn. So I had to leave it downstairs at my front door in my roommate's room. We'd have to shift it over so she can get in a room. And then we have to shift it back so that we can actually get out the freaking apartment. So, the importance of doing this kind of problem. I felt so proud. And then I'm like, oh shit, my math is weak at the moment. A steel pipe is being carried down a hallway, 9 feet wide, so
19 and 16.
yeah, so it's 9 feet wide, 6 6 feet here. And they kind of help you out a lot. They draw it right at the point where it's going to have possibly a problem. And here's the angle. Okay, so show that the length of the pipe in the figure is modeled by the function that. And if it was exactly that long, if it was just a little bit shorter than that probably, then you can make that turn. Right? A little bit longer, you ain't never going to make that turn. Of course, this is excluding the idea of a third dimension, right? Where you could just kind of lift the pipe up and maybe it'll go around, right? Blah, blah, blah. So they give you the answer, which sometimes is bad, because sometimes it's not going to look anything like that until you get done setting it up. So sometimes you're looking at the answer like, how do you get to... No, just screw it. Just look at it later. So the length of this pipe is the whole thing. So the length of the pipe is made up in 2 sections according to my picture, because I have 2 right triangles I'm working with here, really. One right triangle is there, right? And the other one is there. And I could, if you want to, I could even look at this right triangle, so the angle's in there, right?
And then you have another one.
Doesn't really matter. Yeah. And then I could look at, how do I even want to look at this? Yeah, no, you could just look at that one. But let's see. The important part of this problem is making sure that the angle's in the right place according to whatever triangle you're looking at. So I don't know which triangle you want to look at. It doesn't matter. Because all I care about is this length right now for this triangle here, right?
Yeah.
So I can use that triangle or that triangle, and it's going to change my perspective because the angle is going to be in a different place necessarily. So if I want to use this one, seems to be a little easier, then how am I going to represent, and they tell me this is 9 foot here, right? So what trig functions, if I turn this around, let me draw this here, I'm going to turn it like that, theta, this is 9, and I want to know this here, you call this L1. Yeah, so if you say cosecant, what's the cosecant?
It's L over 9.
Good. So it's the hypotenuse is the reverse of the sine, right? So it'll be L1 over 9. So L1 is going to be 9 cosecant theta. And we feel good because I see 9 cosecant theta there staring me in the face, right? If you look at the final answer, it's supposed to have a 9 cosecant theta in it. So the other part probably comes from this dude. Now, your only concern now is how do you work theta into that?
You put it in the, never mind.
And what kind of, I don't know if you guys remember,
It's parallelogram, so you can put it up at the top.
there's a lot of nifty stuff going on here. Yeah, there's parallel lines going on here.
So it goes to
Opposite.
So that's, yeah, exactly. So it's alternate interior angles, right? You could even say, sometimes you got to do something like this. How big is this angle here?
There.
You guys can do it. If that was 20, that would have to be
70?
70, because that's 90, right? So if that was 30, that would have to be
60.
60. So that is theta, so that must be
90 minus
90
90 minus theta. This one has to be
90 minus 70.
vertical angles, right? They're made the same way. If that's 90 minus theta, this must be theta. So if you want to use alternate interior, or if you want to kind of step through the vertical angle that way, you have a couple ways you could do this. Geometry, this is why it's a prereq for this course. And then I can just look at that and do the same thing we just did for that length. I'll call it L2. Crazy enough, right? So that should be plenty to get you guys going. Should be able to figure out that other triangle. And then part B, I think you just graph it. And once you graph it, you can see there's going to be a minimum. Yeah.
Never mind.
Okay, I can do that.
Okay, actually, yeah. So it asks why when it's the minimum. Yeah, I just didn't know how to describe
What's
it.
it say? Why the value of L is the length of the longest pipe that could be carried. Yeah.
So I just don't know what the hell it wants us to write to you. Because if it's any longer than that, it's going to hit the walls. Is that pretty much all you want?
Yeah, you're not going to be able to turn the corner. That's all you gotta say.
Dumb
Yeah.
answer.
There you go, there you go. You gotta
I
like
didn't know if there
that.
was like some
You
mathematical.
gotta like that. You don't get to answer a math question with, otherwise you'll hit the wall. You go in. You know, this time you can't. Otherwise you're gonna put a hole in your wall. Neighbor's not gonna like it. Yeah.
Okay.
I don't say you talk like
was that's simple.
Yeah, yeah. So anything else from homework?
76 on 5-3.
Oh, okay. So on x-intercepts, blah, 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 blah. Okay. 76, this in here, right? Sine of 4x over 2x. Is that the one you're looking at?
Yeah.
Okay. Now that's a very funky function. Just say a word about this real quick. If I let x get really close to 0, why can't I let it be 0?
Because
Yeah. But if I let it get really close to 0, sine of close to 0 is close to 0. And 2x close to 0 is close to 0. So I kind of get 0 over 0, which anybody going into calculus, you'll study that quite a bit, what to do in that case. So the answer here, normally if you divide 0 by something, the answer is 0. And normally if you divide something by 0, the answer is infinity. This has both things going on at the same time, so very often that kind of comes out in the middle somewhere, like at 3. In this case, it would be, what would it be, Jeff? It would be 2, I think.
Yeah.
Yes. Okay. There's a shortcut, anyways. So, did you have to know any of what I just said for this problem? No? Okay, I seem to not care about that fact. So part A says, is it even, odd, or neither? And how do you check for even, odd symmetry? Yeah, so if you plug in f of negative x, what's the sign of the negative? Okay, so it's the negative of what it would normally be, because sine is what kind of symmetry does sine itself have? Odd. Beautiful. Cosine is the one that's got even symmetry. And of course, there are the two negatives. Cancel, so you get right back to what you were. So overall, this whole function has even symmetry. And if you think about it, why does it make sense? The top function has odd symmetry. What's the degree of the bottom?
1.
So it's got odd symmetry. Remember when I said odd was like negative? So it's negative divided by negative.
Positive.
Positive. So it makes sense that it comes out even. Yes, sir?
What would happen if it was cosine?
Would you do this test, and what would happen at this point? Cosine of negative 4x would just become cosine of 4x, because it's got even symmetry, and then the whole thing would be odd. And that would also make sense, because then it would be even divided by odd. Positive divided by negative would be negative. I just said a lot. Okay. So that's all I have to do for that part A, is test for symmetry, and it comes out even. Part B says, find the x-intercepts of the graph of f. And it's got a little calculator symbol next to it, so.
Yeah, I realized I did remember. I was fucking with 75 thinking it was 76.
What's that?
I was messing with 75 thinking it was 76.
Oh,
So that's,
that'll never come out right.
That's the one I was messing with, and it looked way different on the calculator.
Alright, but when you do this, when you graph this guy on the calculator, and if you zoom in, you can use zoom box to zoom in really close to its y-intercept, it should be 2. Yeah. So it's a situation where the 0 on top and the 0 on the bottom kind of bang against each other, and then they agree on 2.
With this one, it like goes down and then it's like.
Yeah, it is kind of cool. Yeah,
Cool.
I like it.
This one?
Because of course, what is x? Sine is going from negative 1 to 1, right? And I keep dividing that by something that's getting bigger and bigger. So that's what we can even call that possibly some kind of damped oscillation. If I pluck a guitar string, it's going to play that, the sound. But of course, what happens over time? It's smaller and smaller and smaller. It's got this dampening thing going on. Yeah. Okay. So anything else from homework? All right, so let's officially talk about section 6.4.
We're going to finish 5 tomorrow. Or work on 5.
We're finished with 5. I don't know if you noticed that.
5.4, that was it.
Yeah, 5.4 was just
Well, 5.4 was just graphs.
graphing, yeah, secant and all kind of stuff.
5.5.
Nope, nope. 5.5 is inverse trig, and so is 6.4.
Oh, okay.
So that's why I was bouncing between them, because they actually did have some separate ideas for a while, and then they hit this section where it was the same damn thing twice, and I'm like, there's no need to do that.
So you're not doing the 6.6? Or is it?
6.4, 6.5, 6.6 we will do. 5 we're done with. Done with 5. So we already talked a little bit about using inverse trig, but we still haven't really taken care of the big problem, which is that a sine function should not have an inverse. Why not?
Because it doesn't pass the other test.
Doesn't pass the horizontal line test. It fails it so bad. It goes through infinite number of times, a horizontal line, right? So that's like the worst you could do with a test. But we did come up with a way to do this. If I just graph one piece of this. If I cut this off, where'd we figure it out? Yeah, I want to cut it in such a way that it passes the horizontal line test, but it also captures all of the possible values. So it doesn't have to go through a whole cycle to capture all the values. Right? So the lowest value is here. So if I do from negative pi over 2, and the highest value is there, it's pi over 2. So I cut it there. I say that's going to be my domain. So for negative pi over 2 less than or equal to x less than or equal to pi over 2, then that is invertible. That passes the horizontal line test. What you really have to understand about this, and this is huge, what I'm about to say. Notice how Jeff is slowly speaking now. If the domain of my sine has to be cut to this, what does that mean about my inverse sine? The domain of sine will be the what for inverse sine?
Same.
Careful.
Oh, the inverse.
Inverses do what with x and y, which means they do the same thing with domain and range.
Flip.
So if the domain of this has to be cut to this, the range of inverse sine will be there. So this is my domain for my sine in order to have inverse. So the inverse sine will have a range of negative pi over 2 to pi over 2. So that's the consequences of forcing this to have an inverse. Which means when I do an inverse sine in the calculator, I have to be careful. It might not be the answer I want. If I'm supposed to be in the second quadrant for an answer, inverse sine will only give me answers in what quadrants?
First.
First?
And second.
No.
And third.
What is negative pi over 2 to pi over 2?
4.
Negative pi over 2 to pi over 2, it'll be first and fourth. Good. So let's check this out real quick. Anybody who has their calculator with them? Well, actually, don't even do it. Well, yeah. For this first part, you shouldn't do it. What's the sine of 3 pi over 4? Yeah. Positive. The over 4 is where the rad 2 over 2. Is everybody with me?
Yep.
Now, in your calculator, do inverse sine of rad 2 over 2. Be really careful with your parentheses.
Yeah, 45.
And depending on which mode you're in, maybe for now degrees is good. Because radians comes out as some decimal, right? They don't just leave the pi. So if you're in degrees, you should be getting 45 degrees. Is that right?
Yeah.
sort of in a way, but no, it's not. If I'm supposed to be in the second quadrant,
Oh,
so it depends on the problem. If you have to have an answer that's in the second quadrant and you use inverse sign to get there, it's not going to give you the right answer. It's actually going to give you a
referencing.
reference angle. Kick ass. So the outputs of basically all inverse trig functions will, in some sense, be a reference angle.
Say that again.
The outputs of every inverse trig function, even the ones that I don't have to worry about cutting the domain, will be, well, I have to cut everybody's domain. Let's start over here. The outputs of every inverse trig function will be, in some sense, a reference angle. If you're lucky, it'll be exactly what you want. If you're not so lucky, it won't be. Right?
And then, according to whatever quadrant it's in, you can figure that out.
Exactly.
Okay.
So if I said, so here's a problem I might give you, a very basic problem. If sine theta is, oh, you can do it, Jeff. Can you? We'll figure it out. Negative root 3 over 2 with theta in quadrant 3. Right? Find theta. So let's see, try to do that. Maybe keep it in degrees for right now. Yeah, it's a 3.
Quadrant 3. Okay.
Quadrant 3. Yeah, I'm sorry. Yeah, quadrant 3. It had to be 3 or 4. And thankfully it didn't at least look like a 4. Right? Why did it have to be 3 or 4? Because sine's only negative 3 and 4. But I agree, it would be nice if I could make the number 3. That would probably be good for my job. So of course, finding theta seems to be a one-step deal, but we just talked about why it really isn't. So what do you get? What do you have to do to this to get theta?
Inverse.
Inverse sine. And when you do the inverse sine of this, what do you get?
60. 60.
So you get, what do you get?
60.
Negative 60.
Negative 60. Good, thank you. Sorry, I want to make that point. Because the answers will always be between negative pi over 2 and pi over 2. You will sometimes get these negative angles, right? We're supposed to be in quadrant 3, of course. So what's the real angle going to be? What am I going to do with that 60?
Plus 180. Oh no, minus 1.
Yeah, it's supposed to be in quadrant 3, so I'm going to add it to 180. So the angle that I really want would be what?
240.
So this would be the reference angle. And the real angle I want is 240 degrees. Yeah, or negative. Any coterminal angle, it would be acceptable. Maybe somebody give me 1100 and something degrees now. Yeah.
It didn't matter that it was negative. You just add what the value was. Correct?
Yeah, again, inverse sine it's not inverse sine's fault, and it's not our fault. We had to cut it to make it have an inverse. So we just have to now be able to interpret the output. The fact that it's negative is really just telling me that I'm in the third or fourth quadrant in a way, right? So if it comes out positive, that's trying to tell me I'm in the first or second quadrant, and it's saying, you're the human, you figure it out. Yeah.
So to make it fair game, they would have to give us a quadrant number.
I'd have to give you some way of figuring it out. Yeah, exactly. Do you guys realize this? So it is just as easy. The first step, just do the inverse in your calculator. But then you got to think, is there something in the problem that tells me I'm supposed to be in a certain quadrant? Because maybe you're not in the quadrant you're supposed to be in. Okay, I can't read most of you. Okay. Oh, it's driving me crazy. All right. So here, you guys try these. Let's expand. Real quick, before I give you some problems to try. We've only got sine under our belt. What about cosine? So it looks like You can do this job. Wow. So where do you think I want to cut this dude?
Right there.
Negative pi.
Negative whatever.
Pi over 2.
If I do from negative to positive, it's going to suck. So it pretty much has to start at 0, right?
Yeah.
And then how far you have to go. So that's what it captures as most positive. And now I want to go as far until I get its most negative. And don't look at my scale too much.
It's only pi.
And,
Yeah, it's going to be pi.
and it doesn't matter if you pick one or the other, because obviously they look like the same.
So let me say it this way. If you would have been around when they were first coming up with what it had to be, it didn't matter if you picked 0 to pi or negative pi to 0. Can you understand why they maybe picked this one?
Because it's positive.
Because it's all positive. But everything would have been exactly the same if they would have been back here. They would have still been reference angles. You would have still had to do something to figure it out. But they said, let's have the positive side.
We like to do laser.
We're smart about what we do. That's different from lazy. Just barely. So the inverse cosine is then going to have what range?
0 to pi.
Exactly, 0 to pi. So we can do all the same kind of stuff we just did with sine. You just have to be careful about what angle. So it's not really going to be a reference angle here, truly. And neither was that really, because you had negative angles. And of course, a reference angle is supposed to be from 0 to pi over 2. But this is going to have outputs like 120. It could be in the second quadrant, right? And maybe you're supposed to be in the third quadrant or somewhere else. Okay, maybe. So you just have to pay attention to what quadrant you're supposed to be in and go from there. Okay. But it's a lot like sine. It covers its positive. Let me draw the unit circle here. It covers the positive and the negative for a cosine. Right? It's got to. So let's try some of these. So throw one freaky one at you. Wow, that was pretty good.
Bless you.
Yeah.
Oh yeah.
You do it, man.
Now, some of you guys might realize, I'm going to do this on some tests. I might give you this problem and say you cannot use your calculator. In which case you would just use the radians that you know it's supposed to be. So, right? That one, yeah. You got to use your calculator. Just plug it in the damn calculator and make sure you end up in the right quadrant. No, why would you add 182? So it's like a...
See?
You add 90 to 60.
Yeah, why? So...
Why?
There's just 90 to do it.
Exactly. So it's supposed to be... So again, that's not going to be true reference angles, right? So you think about the reference angle for that angle and you make it go into the correct quadrant. So what would the reference angle be for that angle you got?
60 degrees.
60. So now take that same thing and just put it down there.
Exactly 192.
So here's how this works. So cosine's a little bit different than sine. So if you do this, you get theta equal to
120.
120. And really, if it comes out, if the answer comes out in the second quadrant, it's trying to tell you it could be second or third. Right? Because that's where cosine's negative. If the answer comes out positive, it could be in the first or fourth. So you know this is supposed to be in the third quadrant. You're not supposed to add 90 or 180 or something. I mean, it comes out. It's almost right what you did, but you got to be careful. The reference angle for this angle would be 60. It's not supposed to be quadrant 2, but it's supposed to have a reference angle of 60. So what would it be here if it's a reference angle of 60? 180 plus 60? 240.
If you did it in rad,
If you did it in rad, it would just be 2 pi over 3 would be this. And then you have a pi over 3 reference angle. You throw that same reference angle down in quadrant 3.
4 pi over
4 pi over 3. Exactly.
So
Is it
should
better?
should I not think of it as 360 minus 120?
So, I mean, and that would, if it was, well, let's see how this one comes out. So what do you get here if you do this?
30.
30.
Yeah, so you get 30 degrees. And then you have to actually push it down into quadrant 4.
So 330.
Yes, and 360 minus 30 is
330.
330. Cool. So you look at the answer, that's kind of like the same reference angle this guy has is the one that my answer is supposed to have. This might be my answer. If I would have just said in quadrant 2, I could have stopped. Because it came out in quadrant 2, but it's not. Yeah.
Could I also just put negative 30 for quadrant 4? Or do you want it positive?
Yeah, that's fine. If I don't specify, it's got to be positive. Yeah. Again, if you're really comfortable with this and you just want to give me some crazy, like 8 revolutions later coterminal angle, I can't argue with it if I didn't. Sometimes I will say the answer must be between 0 and 2 pi. In which case I couldn't take a negative angle, right? How are we doing so far? So this first step's the same. You still do the inverse cosine, but then it's how to interpret this. This is not the same as sine. Sine was easier. Even though some of them are negative, I could look at all of them like direct reference angles. This gave me 120. That's not a reference angle. Well, what's this guy's reference angle? 60. That's the one I want to use to push me into the right quadrant.
No, that one.
So this one, what do you get? You know, you're just going to get something,
6.38.
okay?
No,
No, it's fine.
Okay.
It should be small. I don't know what it really is, but it should be small. Sine is 0 at 0, and this is not anywhere close to 1. It's close to 0, so the answer should be close to 0 degrees. So 6 point, whatever the hell you said.
38.
38 degrees. And if I want to be in quadrant 2,
So use that as a reference angle.
use that as a reference
So then
angle.
minus 180.
So draw a little picture. I want to be here, so I want to go back this much from 180, so 180 minus this.
173, 160.
So if you don't draw pictures to help you through this work, I don't understand you. Right? The pictures really anchor us as to what we're supposed to do. Yeah.
How'd you get the 120? Because cosine of negative 1 half is negative 60.
No, the reference angle.
What's happening?
Where'd you get the 120?
If you do the inverse cosine in negative 1/2 in your calculator,
Oh.
yeah. Now this you should be able to, if I just told you this and this, you could actually do it without using inverse trig at all, right? I mean, you shouldn't have to do that. I mean, if I said the cosine of this angle is negative 1/2 and it's in quadrant 3, the reference angle has to give you 1/2, and that's going to be a 60-degree angle, and then go in quadrant 3, you would just do 60 past, yeah. So you could actually do this whole problem without using inverse trig. I'm just trying to get us used to inverse trig right now. Using the buttons and stuff and interpreting what we get. Yeah.
So when it comes to like that sine, what if you did it in rad? How would
Then it would be pi minus whatever you got.
Okay, that's it, just be pi.
That's
minus the approximate decimal or whatever.
So there's a problem in homework a while back. There's only one of these, but you had to do 10 minus 2 pi to be
Yeah.
coterminal, whatever the hell it was. I can't remember the idea. Right, and it was weird because we weren't used to seeing 10, and that was radians. But so now we're doing the same kind of thing. Depending on if I'm in radians or degrees, I just use the appropriate thing for that. In this case, I want the negative x part, so it's going to be 180, or it's going to be pi in radians. Cool, maybe. Okay. So one more idea. Oh, well, 2 more ideas. Now, what does this open up here? What trig function do I want to use? Yeah, it's going to be sine. It gets me started. So sine theta equals 2/7. So then it becomes a lot like that last one we did. Inverse sine, depending on if I say degrees or radians. So if you do the inverse sine of both sides, what do you guys get?
16.60.
And the nice thing here is you just have to make sure that your angle is where? What's the largest angle in a triangle? Well, a right triangle especially. The largest it could be,
89.
yeah, 89.999. Because then you have to leave a little bit for the last dude, right? Does it make sense? So that you have to make sure your answer comes out in between 0 and 9. Cool, okay. So it's nice when you have physical properties like this, you don't have to worry about quadrants. They have to actually make physical sense. So, any triangle setup I give you, it's almost going to feel like what we've already done. Instead of putting an angle, you're just going to put the symbol and solve for it. So we've already done problems like this before. It's just the unknown is now something else. Okay, cool. So what about like tangent and cotangent? Those are a little bit easier. I still have to cut the domain, but it's a lot simpler to see what it's going to be. What does tangent do again? Where is its main asymptotes? Negative pi over 2? Pi over 2. And those are because what's on the bottom of tangent, if I rewrote it, it's what over what? Tangent is sine over cosine. And where's cosine 0?
Pi over 2.
Pi over 2, negative pi over 2, for example, right? So that's why tangent has asymptotes there, because cosine is on its bottom, right? Sounded strange for a little, not judge. And of course it does this picture forever, but the decision about where to cut the domain is given to us already. We're going to cut the domain from negative pi over 2 to pi over 2, right? And cotangent, you guys remember what cotangent was all about?
It's that.
Good, it's the reverse of that shape, and where is its main asymptotes? 0 and pi. It still has to have a pi period. And it's the reverse of this dude. Yeah. So its inverse is going to give you angles between 0 and pi. So it feels a lot like sine and cosine, right? Let me say that again. Sine gives you angles, but inverse sine gives you negative pi over 2 to pi over 2. So will inverse tangent.
Okay.
Inverse cotangent will give you the same thing that inverse cosine does, right? Just because that's where we had to truncate their domains.
Why does it start at 0 and go to pi?
Because cotangent has what on the bottom?
Sine.
Sine, and sine is 0 at 0 and pi, for example. And again, like I think somebody pointed out, we could have went to negative pi, but we'd rather have our base one be positive stuff. Yeah. Okay, cool. So they'll work the exact same way as the cosine and sine stuff. So the very last thing here is, let me give you a remarkably simple problem, and then we'll show you how that becomes much more complicated. All right, that's remarkably easy, right?
Cancel.
Cancel. So, bam, you get 4 sevens. Okay, maybe. Easy, easy. So what have I said? Sine of inverse cosine of 4 sevens. Nah. So here's what I want you to realize. And this is what you use in here, in calculus, in calc 2, sometimes in calc 3. If you're going that far, if you're not going that far, you need it here anyway. This here, I really want this to make sense. Do you see how the first statement we got came from this triangle? And then we did this. So this by itself, if I work backwards, this represents that triangle. Or let me say it better, is represented by this triangle. That statement is represented by that triangle.
Oh, so it's
What's the answer to an inverse trig?
a triangle.
An angle. So a way to represent this is to draw a triangle with that angle in the base with the ratio matching what sine would need. That's how you can represent an inverse trig visually. So if I draw this dude's triangle, asking what the sine is freaking easy. So what would this triangle look like? What side should be what? To make cosine 4 over 7.
7.
The bottom's 4. 7's got to be hypotenuse. Now it's old. Now it's old. Old news. How do I find the sine of this angle? I need this side. Good. And what's that side going to be? Square root of 49 minus 16, which is 33.
33.
So what's the sine of that?
33 over 7.
Yeah, root 33 over 7. Done. Done. Finished. Next. So if I give you an inverse trig, it represents an angle. And any angle I can look at as living inside some kind of triangle, because the trig functions are all about ratios of sides of triangles. Now I could have drawn a triangle that had 8 and 14 and 20, but I'm going to draw the lowest, the lowest terms. Yeah.
You didn't do it with your calculator too, right? With the inverse none of that.
Of course you could. But you know what I'm going to do. Okay. And real quick, here, not because of what you just asked, but I love that you just asked that question. Because what if I ask you this here? Tangent of the inverse cosecant of x over, how evil do I, screw it, I'll be evil, sure.
I can't use your calculator.
So don't overthink this. It's really easy to do. Which side should be which? Cosecant is related to sine. So
X plus 1 is the hypotenuse.
No, x is the hypotenuse.
good.
No, that's right.
So before anybody yells at me, these don't have to necessarily be positive for this problem. Right? So don't tell me that this side is longer than that, because if that's negative 0.6, well, it still won't work. Screw it. Doesn't matter. So how do I get this last side?
X minus x plus 1.
I think it goes squared minus.
Yeah, square root of x squared minus x plus 1 squared. And why do I need that side?
Because that's tan.
Tangent would be that over that.
Yeah.
Cool. So I just got to be careful about that making it work. But that's how you do it if I have variable expressions in there. Variables are just numbers I don't know yet. I'm going to do the exact same thing. They're not any different. Yeah.
Okay, there's one thing in there that just seems impossible. How is there x plus 1 on a leg
That's what I just said. But,
It's still,
yeah.
Not supposed to work out.
So this would have been this way. Right.
so it's still.
Yeah, it would, same idea, same process. But as I was setting this up, I changed my mind at one point and forgot later. So anyway, same idea. All I care about is a freaking idea. Do you know how to do these problems? And if I have variable expressions in here, they work the exact same way. Cool.
And the hypotenuse is supposed to be the longest angle then. How is
Sorry,
you're going too fast for me.
Ryan.
Okay. I think if x were negative, it would have been like negative 0.6. It would have been negative 0.6 over negative 0.4, which is bigger than 1. It would be fine for Kusa.
But how did you just change it?
Because I have that power. Yeah. All right, I have a feeling that might be enough. So I'll see you guys tomorrow.
I need to explain everything's in that box. It's going way too fast.
What you gotta do is tell me that, Chris. So, how are we up here?
Usually with
So if you push it down this way, this is right here. So that means that if I give you this,
It just seems like here, it's like
then over here you're like just use fucking logic. It's like
because
what if you throw that
because watch this. I had to use a calculator for this because I wanted to know exactly what theta was. If all I wanted to know was what the cosine of theta is, all I need is the left side. There you go. So then I wouldn't have to use the calculator, would I? So over here, I'm not asking you what the angle is, what the answer to this is. I'm asking you what's the sine of this angle. So if I can set up a triangle that represents this angle, which is right here, right? Because the cosine of theta would be 4 over 7. So that angle is the inverse cosine. The triangle represents this. Then I can figure out the sine of that angle just by figuring out the side that I need. So I don't have to use a calculator for this. So even here, whoever said they can use a calculator for this, it's true. You can get some decimal answer. I'm not going to want a decimal answer. I want the exact answer. So this represents an angle.
Right.
And all I want is the tangent of the angle. So if I can figure out what the sides that the tangent wants to make the ratio of, I can get the answer. So I set up the triangle that this represents, and then just get the last side I need and make the ratio. So that's how any of these kind of problems can work. Now these are the same, and let it be easy, they just cancel.
All right, so since this is the answer to what this was, which was x plus 1.
Yeah. So this would be square root of x squared plus 2x plus 1 minus x squared, because c squared minus, yeah. Okay. Well, I'm going to assume people can FOIL, Chris.
All right, no, I got you. Just
And then if I want the tangent of this,
in order for me to understand it, I need to do it. So that's the problem.
of course.
But I'm not a fast writer. I'm trying to get it all down to set it up so I can do it. It's just.
but see, that's